Hi, welcome to another Calculus or All video short. And today's topic is investigating the derivative of a function that's in the form of x to the n. This is called the power rule. Now what we're looking for is a shortcut method of doing the derivative of any term in a polynomial that's written in the form of x to the n. That is x, or maybe x squared, or x cubed, or x to 115. Now, we already know how to do the derivative using our limit definition. We're comfortable with that limit definition. But what we would like to do is see if we can derive a shortcut technique so that we never have to apply that limit definition again. Well, the way to approach this is create an abstract function that is x to the n. So n is any variable that we so choose, but we'll leave it as n at the moment. So we'll take our limit definition, and what we will do is we will let our function f of x equal x to the n. Now we need the derivative, so we'll apply a limit definition to that. We'll substitute x plus h into our function, and I get x plus h to the n. And this is where we have our dilemma. We need to expand out x plus h to the n. Now it was nice if n was 3, because we know how to do that. If n was 4, we can do that. But n is n. It's a variable. When do we stop? Lucky for us, there's an approach, and this is called the binomial expansion. So we're going to binomially expand x plus h to the n. Now, not to scare you, but I'll put on the expansion in blue here. Now you may not be familiar with this, but there's actually a pattern. You'll see things in brackets. Look at the first term. You see an n with a 0. This is n choose 0. The next term is just n choose 1. The next term will be n choose 2. And so on and so on and so on. And I'll finally end up with the final term being n choose n. Well, n choose 0 or n choose 1, these are just techniques in the field of combinatorics. Lucky for us, all we're interested in is the first two terms and the last term. And n choose 0 is just 1, n choose 1 is just n, and the final one, n choose n, is also just 1. Now look at the x and the h in each of the terms. There's also a pattern there. X starts with an exponent of n, and then the next term is down by 1, so it's n minus 1, and the next term is down by 2, and it'll be down by 3, and it goes all the way down to the exponent equals 0 in the last term. Whereas the h, the exponent starts at 0, and the next term it goes up by 1, so it's h. And the next term it goes up again by 1, so it's h squared, and it goes all the way up until the nth term where h is to the n. Now, because the first, the second, and the last term are easy to evaluate because we know what the n choose 0 is, and the n choose 1, and the n choose n is, we can simplify our expression. So h of the 0 is just 1, and then we notice n choose 0 is just 1. So my first term is just x to the n. Similarly, n choose 1 is just n, and then x to the n minus 1, h to the 1. Then I get all these ugly terms in between, and my final term, again, n choose n was just 1, x to the 0 also is just 1, and so I end up with just an h to the n. Now it's still quite complicated in all the terms in between, but all I care about is the first two and the last term. Now look at the first term, x to the n, and if you remember from our limit definition, we subtract f of x, which is also x to the n. So my first term and my yellow term, they cancel each other out. So my expression has just gone down and simplified just a bit. Now every term here, as you'll notice in this limit, has an h, and I'm dividing by h. So I can cancel out an h from every single term. So let's get rid of these little h's. And when I do that, my expression simplifies a bit more. Now it's still quite complicated, but I'm not worried about this because I'm trying to determine the limit as h goes to 0. And if you notice very carefully, every term has an h except the first term. So when h goes to 0 and I multiply it by 0, those terms disappear, and all I end up with is the first term. So as I allow the h to go to 0, my expression simplifies to n times x to the n minus 1. This is the derivative of f of x, which equals x to the n, is just n times x to the n minus 1. The exponent goes in front of the x, and the exponent then is knocked down by 1 on the x. So let's write this as a generic form. So given a function which is in the form of f of x equals x to the n, my derivative f prime of x is simply n times x to the n minus 1. And those we can do in our head. So let's look at a nice easy example. Let's take a function f of x equals x to the 100. And we're asked to find a derivative that is f prime of x. But all we need to do is put the 100 in front of the x, take the exponent 100, decrease it by 1, which is 99, and so our derivative is simply f prime of x equals 100 x to the 99. Can't get much more simpler than that. Let's look at a whole bunch more little fast derivatives that we can actually do in our head. So this is a tricky one. F of x equals x by itself. Well, this is really x to the 1, so I'll put a 1 in front of the x, then decrease the exponent by 1, so 1 minus 1 is 0. X to the 0 is 1, and then 1 times 1 is 1, so the derivative of f of x equals x is simply 1. How about x to the 5? Well, this derivative is just 5 times x to the 4. I can even handle negative exponents. So that the function is f of x equals x to the minus 3. Then its derivative is going to be minus 3 times x to the minus 3 minus 1, which is minus 4. How about f of x equals x to the minus 20? Well, our derivative, f prime of x, is then minus 20 times x to the minus 21. I can even do some really cool stuff. How about f of x equals x to the pi? Then its derivative, f prime of x, is equal to pi times x to the pi minus 1. This is the power rule. It's very, very simple to use, and most questions you can now do in your head without having to apply the limit definition. Hopefully this was helpful. Thank you for watching.